This is Professor Coles from Marine Hydrodynamics and Propulsion. This is the second little video tutorial for the boundary layer computing exercise for the class. So in the first part we logged into the cluster and we edited some files to put in the parameters that each of us will need for our specific Reynolds number runs, and whether that's turbulent or laminar. In my case it was a million was a Reynolds, and I made it laminar, which is definitely a stretch for laminar boundary layer. And then ran the code. We kind of looked at some of the output for fun, and then we ran two post-processing scripts, one which told us the final drag that was calculated, which we assumed to have reached a steady state, and the other which generated a PNG file which will plot that history of the drag. And we also looked at the, I guess it's still up here, in the subdirectory of our main run directory here with all the stuff in. There's a subdirectory VTK, and in VTK was two files. The first is the initial condition, contains all the information about the fields, basically U and P, or velocity and pressure fields we can use to plot a solution in space. This is my final solution. As I mentioned, this number is going to be different for each of you. Whatever the large, the non-zero number there is VTK file, and transfer it over. And WinSCP, you would have just dragged it over to your computer. In on the Mac, if you're not using Fuse, you would have used Secure Copy to copy it to your machine. That's what I just did. So I'm on my local Mac here in this lower window. This is a terminal on my Mac. What I'm going to do is, well, I tend to use every terminal for everything, so I'm going to open it up into a Finder, which is probably more people are used to. So I'll open up the Finder. So here's this file, drag history PNG, which will open it up, and preview will pop that open. And this shows the iteration number, so it's iterating to try to find a solution, a steady state solution. You can see this reaching a steady state. The first iteration produced a drag here, which actually is not too far from reality, which is pretty amazing. And then it converged over the course of 700 iterations to essentially a steady state value here, which I had recorded over here. 0.0072 was my steady state drag. So this just confirms that it converged. Later, when we start working with airfoils, we're going to be using a steady state solver, and if the flow over the airfoil is not inherently steady state, which generally happens if the angle of attack is too high and it's starting to stall, then we're not using the right flow solver for that. We should be using a transient or unsteady flow solver, which is quite expensive. So we're sticking with steady state solutions. That flow solver will fail to find a steady state solution because there is not one. And you will see the drag or lift history still oscillating at the end, which indicates it never really found a value. Here we don't seem to have any problem. I don't expect any in your cases, any problem in your cases. So this just confirms that this value here is the steady state solution of this system. Now I'm going to plot it and using Visit. So I gave you links to download Visit. We'll be using Visit, and we might use ParaView too in the class. They're pretty similar. I don't want to say they're similar. I think they have some theoretical differences, but the ideas are fairly similar at a kind of a superficial level. So I'm going to open Visit up here. You would just open from your. You can open it from applications too. I just do everything from the terminal. So start the software. You see it pop up. It takes a little while. And we're going to visualize this output. Now I opened it from this directory, so I already have it here. So let me open it, and I'm just going to open this from somewhere, the wrong location. So if you just started the application not in that directory, then you would, now I would have to find my way to File, Open File. I want to open that VTK file. I'm not really sure where. I don't know where that ended up. It must be in, sorry, 1 second here. Okay, so it is in, where is it? Documents. Here it is, mhp490 VTK. Open that up. Okay, so it's loading. Now, you can do lots of stuff. This is my main plot window. What I'm going to do first for you is plot the mesh. So I'm going to say add, mesh, mesh. Click the mesh. Mesh is a very strange word to say. And then I'm going to hit draw. There it is. Okay. So this is a mesh plot. See, viewed from the side, you can see what I did is I scrunched it down near the bottom boundary layer. And basically in each of these volumes, let me zoom into them. There's a little looking glass up here for zooming. I'm going to zoom in just somewhere down here. And this is actually the axis you're seeing here, but you can see these little cells near the plate. So in each of these cells, and they're three-dimensional, which I'll show you in a second, we're solving, or OpenFOAM is solving conservation of mass through that cell and momentum through that cell. So in each of those cells, you're doing a mass and momentum balance. It's basically what CFD does in this type of application. So let me zoom back out. So I zoomed in here. You can always get back out if you go up here. They have these kind of different view options at the top of the screen. The camera, it's got kind of a strange X on it, but if I put the mouse up here, we'll say reset view. Now we're back to normal. Now I'm going to click on it, rotate. And I'm not sure about the mouse commands in Windows, but for those of you used to dealing with graphics and stuff, you'd be fine. So I'm going to rotate. Oh, obviously I'm not fine. I'm going to go back here. I'm still stuck in my looking glass, so it's waiting for a zoom. I'm going to hit on here, which is the compass for navigation. I'll rotate, and you'll see this domain is actually 3D. Now I have it set up so the flow is going in this left face, out this right face. It's flowing over the plate, which is at the bottom. Now I've set it up so the boundary conditions up so the flow's coming in. This first, the dimension of the domain is too long, but as I mentioned before, the plate is only of length 1. The real plate starts here at 1. Prior to that is inviscid flow. It's a slip condition at the wall. I wanted the flow to come in and hit the edge of the plate, sort of get itself set up, and hit the plate and begin the no slip condition. So the boundary layer begins here. The real plate begins here. Now, OpenFOAM is kind of a weird code in the sense it doesn't really have a 2D, a true two-dimensional version. It just solves 3D where there's nothing going on in the lateral direction. So you see that there's lots of cells in the X direction. There's a lot of cells in the Y direction, which is normal to the plate. There is one cell in the Z direction. There's not much going on there because we don't want any variation in Z. It's supposed to be 2D. So what I'm going to do is take this 3D. I only care about 2D. I'm going to slice it. So I'm going to go to Operators, Slicing, Slice. Now down here, these two buttons right here indicate Apply Operators to all plots. That means anything I plot from now on is going to get sliced in the same manner. I don't have to slice everything. One slice will work. I'm going to open this up to give me some options. I'm going to click on the slice. Obviously we've lost everything. I'm not sure why, but we'll find out why. I'll click on the slice. I think it's intersecting with the wrong plane. I want to slice with the Z plane. So actually, let me go back. Let me kill the slice for a second and redraw. Z varies from from minus 0.5 to 0.5. So a Z plane at Z equals 0, a plane at Z equals 0 is going to exactly cut this box in half. That's what I'm going to do. Slicing, slice. Click on the slice. By default, it's trying to slice in Y. I'd rather slice in Z. This intercept is where the plane is located. Z equals 0 is what I wanted. Now I hit Apply, Close, and it's sort of waiting. It's in this green state. I'm going to hit Draw. There it is. So that's actually a 2D slice to the domain. Now once I plot stuff, I can keep it around, but I don't have to look at everything at the same time. So what I'm going to do is this one here is toggled. I'm going to hit Hide Show. I'm going to hide it. So it'll disappear, but it's still there if I want to display it or hide it. Now I'm going to add a new variable. Let's see. I want to look at the U velocity, pseudo color, U magnitude. I'm going to hit Draw. Now it's already sliced. I don't have to do anything. Now there is a boundary layer here. If I zoom in, we will see it. We'll see it more when we contour, but it's kind of hard to see. It's pretty thin, and very thin, obviously, and goes to 0.5 quite quickly, and then slowly up towards 1. So the free stream velocity is about 1. It's 0 at the plate. That's the boundary condition. So what I'm going to do is change. I'm going to zoom back out to my full view. So this is the whole domain, 0 to 2 and 0 to 1 in Y. And again, I can click on my mesh and bring it back on there if I want to see it. Show, there's the mesh, but it kind of makes it hard to see to render the velocity. So I'm going to hide it again. I'm going to open up my plotting. So they call it pseudo color. This is the color scheme used for the velocity. I'm just going to change the bounds. It's using the original data for bounds. The bounds basically 0 is assigned blue and 1.04 is assigned red. But 0 to 0.5 is contained, that velocity range is contained to an extremely small, basically one cell distance. So I want to look at starting from 0.5, so the minimum of 0.5 up to the maximum of the data, which will be about 1. I hit apply, and now you can see better the boundary layer down here. What I'm going to do, we want to plot delta 99, the extents of the boundary layer. Now delta 99 is, that's one of the definitions we use for boundary layer thickness, where the velocity goes to 99% of the free stream value. Here the free stream value is 1. So we want to draw a velocity contour of the velocity where the velocity is equal to a value of 0.99. So a contour being a line of constant value. In this case, velocity. So again, I'm going to add something new. Add contour U magnitude. So the velocity equal 0.99. I'm going to open that up. I'll draw. I'm not sure what it's going to do. I drew a bunch of contours, but they're none of the ones that I actually wanted. So I'm going to open that up, change the contour options. So again, it's already sliced here. It's already added the slice operator to all these. I just had to do the first one, and now I add anything on here and it automatically slices it. Contour. All right, so it's doing 10 different contours. I don't really want that. I want to set a value of 0.99. I want one contour with this value. Now I have a red background, so a white line might look good. So I'm going to go single. Click on this. I'm going to pick white color here. So it's going to make a white line. I want to make a nice thick line. I'm going to change the line width 4. So that's what I did with contour. So again, I'm selecting one value, 0.99. Oops, 0.99. So this is the definition of delta 99, where the velocity goes to 99% free stream. Here the value is 0.99. I change it to a single white color so I can see something. Now I hit apply. And there you see it. That's the delta 99 boundary layer in this domain on top of the rendered contours. So you can kind of see how it grows. This is the square root of x. This is a laminar boundary layer, and the thickness of it grows with the square root of x. This looks just like a square root function here. And it's actually fairly thick by the end of the plate. At this low Reynolds number, we have a fairly thick boundary layer. And I'll try one more thing. I don't think it's going to render well here, but I'll give it a try. So what I'm going to do is hide these. Actually, let's first, to complete the assignment, I want to print this window. There's two ways I could do it. I could just do a screenshot. In Mac, you hit Command-Shift-4, and then you can just draw the screenshot. It should pop up over here somewhere. There it is. So I can make a screenshot of this. Also, I can save it to a window. So what you do is you go File, Set Save Options. Now I need a file name. We'll call it, I don't know, a boundary layer. Doesn't really matter. Output files to current directory. So it's going to dump in whatever directory I launched visit from, I believe. So let me actually change that. Let's output it to this directory where I have my files in here. Okay, so I selected the directory. I'm going to save a JPEG, and that's it. Apply. Now I can hit save. Okay, and it dumped the window. Now I go here in my Mac Finder. I see a new file has arrived. It's this JPEG thing with a funny name. I'll open it up, and there it is. That's what I'd like you to turn in with your homework assignment. All right, so let's just do one more thing. I'm not sure it's going to work, but let's give it a try. What I'm going to do is hide this and hide this. So I have nothing now. I'm going to add in the vectors. Oops, let me just do that a little slower here. Add vector U, draw. Okay, an awful lot of vectors. Now, what a mess. So let's open up the vectors, see if I can get them to plot how I would like them to. Let me go with a stride of 10. So instead of doing a fixed number, which is sort of randomly located throughout the mesh, I'm going to do a stride. And what they mean by stride, if I do a stride of 1, that means I'm plotting every single vector, which might be a lot. Okay. But if I do a stride of 10, it basically grabs every 10th vector and plots that. Okay, that's what I wanted to have happen. So now I'm going to do a zoom in. I'm not really keen on them being red, but somehow you can change the color of vectors. How about this? Okay, you can play with this stuff, and I'm going to zoom in here with my little zoom magnifying glass and plot this. Now all the heads of the vectors are stuck together, so if I go to glyphs, let's see here, draw head is an option. I'm going to get rid of it, apply, and now you can kind of see, it's not well plotted, but you can kind of see the boundary layer right here going down towards 0. That's the boundary layer of the flow. I think that's all I wanted to show you from Visit, and I will quit, and that's the end of the tutorial.